Okay, thank you. Thanks for the invitation. It's a very nice event and a nice place. I'm very glad to be here for this every 10-year conference. And today I will report a recent joint work with Shouwu Zhang on generic positivity of the Beilinson-Bloch height. We so far achieved some results for Gross-Schoen cycles and Ceresa cycles, and hopefully this project can continue to show the positivity of general Beilinson-Bloch heights. I'm going to start with something maybe you're more familiar with. That's the weight height defined by André White in 1922. I thought in 1928, he defined height functions to measure the size of algebraic points in the purpose of proving moduli theorem. For Q points or just rational numbers, it's very easy. It's just the maximum of the numerator and denominator, taking the absolute value and then take the log. And for points on P and Q, you just take coordinates which are integers and co-prime to each other, and then you take log max of the absolute values of them. For arbitrary number fields, because the class number may not be 1, so you need to do something slightly more complicated to consider all the places and do this sum. But nevertheless, the definition itself is not so complicated. And this is called the logarithmic weight height, or we would just call them weight height in this talk. Just by definition, first of all, this definition is independent of the choice of the coordinates, the last one. By definition, we can prove two important properties. With the proofs are not so hard, but they are very important in the study of height theory. One of them is the positivity. So this weight height is always bounded below from 0, because you can always take one of the coordinates to be 1. And later on, Northcott proved this important finiteness properties, claiming that there are only finitely many points of bounded height and bounded degree. This finiteness property, many different time problems, finiteness results of different time problems can be reduced to this Northcott property. It boils down to that in the end. So this is the weight height. And now let's pass from projective space to algebraic projective varieties. If we have a projective variety defined over a number field, then we can first of all embed it into a projective space for large enough. Then we can compose this embedding with the weight height to get a naive height function on the set of algebraic points on X. So, but however, the embedding is not unique. It depends on the choice of a very ample line bundle, and also depends on the choice of the basis of global sections. So we have many different embeddings. They will give us different functions here, but all these functions, they differ from a bounded one. So having a projective variety and an ample line bundle on it, we do have a different, having a projective variety, we do have a function on the set of algebraic points on X, but well-defined up to a bounded function. Now, because this function is obtained from the weight height, it still satisfies these two good properties. But the first one needs to be changed to bounded from below, because now it doesn't make sense to say whether it's positive or not, because it's only well-defined up to a bounded function. So now we still have this bounded from below property and Northcott property, which is unchanged. Still the two very important properties here. Okay, now let's make it a little bit more abstract. In the abstract setting, what are we saying? Let's take a quasi-projective variety defined over Q bar, so defined over some number field, and we take any function on the set of algebraic points on X to R. And we call this function to be a dominant height if it has a lower bound and satisfies the Northcott property, which is make this definition, we call it a dominant height if it satisfies these two good properties. And here are two famous examples. The first example is the Nihon-Tate height on abelian varieties. So this is a genuine function on the set of algebraic points on abelian varieties to real numbers. And this has a lower bound, 0. Better, we know what points have height 0. These are exactly the torsion points. And this height function can be used in the proof of model-weight theorem. It simplifies some part of the proof, at least, but it also appears in the formulation of the Birch and Schwitten-Dye conjecture, at least some version of it. Okay, it's really the value of the L function or derivative of the L function. And another example is on the modulus space. We do want to study modulus spaces. And here in this talk, I'm going to fix the modulus space to be the one parametrizing smooth projective curves of genus G. And later on, G will be always at least 2. And this space exists by the linear manifold. And we do have also a genuine function, Falting's height function, from it. It sends each curve here to the Falting's height of the Jacobian. And this function, this Falting's height, was defined by Faltings in his famous paper to prove the model conjecture, and this function plays an important role. Okay, one of the main results in the paper is that this function thus defined is a dominant height, by comparing it with some other, with some naive height function. Okay. So we do have these two examples. They are genuine functions instead of just functions well-defined up to a bounded one. Okay, now these functions are on points of varieties. Can we extend them to higher cycles? And this question was asked and first of all studied independently by Beilinson and Bloch in the 80s. They try to extend height from points to height of higher cycles, which are homologically trivial. They call them now we call them the Beilinson-Bloch height. This is conjecturally defined in their works, but in some cases they are unconditionally defined. For example, in some cases by Gross-Schoen, Kuhneman, and Shouwu Zhang. A few cases like I'm gonna explain Gross-Schoen especially. And then they ask a lot of questions about this Beilinson-Bloch height. For example, is it always non-negative, the positivity? And they even conjecture that it's 0 if and only if the cycle is torsion in a Chow group. The conjecture is known in only very few cases, some sporadic families. And then they ask whether the Chow group has finite rank, or the homological trivial part of the Chow group have finite rank or not. And they also formulate a generalized version of the BSD conjecture. But all these are very little is known about these things. And even for positivity result, very little is known. Here are some examples where this is unconditionally defined. I'm going to show two examples. That's the Gross-Schoen and Ceresa cycles, which will be the main objects in this talk. So for this, we fix a smooth projective curve of genus at least 2, and then fix a point which is sort of canonical point. That's a divisor of degree 1, which is the canonical divisor divided by 2g minus 2. We have finitely many choices, but they differ from torsion. So for what I'm going to say later on, it doesn't matter if they differ from torsion. And the Gross-Schoen cycle is a one cycle on C cube. It is called the modified diagonal. It's defined in this picture here. So I'm drawing this cube for C cube. Each direction represents a C, and here we base it at a point C. This is like the origin. And now we have the diagonal, which is the actual diagonal in the 3 directions. That's delta 1, 2, 3. And then we can fix one coordinate to be this C and consider those partial diagonals. And you have the purple one, the orange one, and the blue one. So we fix one coordinate to be C and take the diagonal. And we also have the green ones, which are we fix 2 coordinates to be C. So that's just the curve. And now we have these partial diagonals, and we do an alternating sum. And this is called a modified diagonal. This is a one cycle on C cube. And one can show that it is homologically trivial, meaning that the image under the cycle class map is 0. Another cycle which is closely related is the Ceresa cycle. It's defined as follows. It's a one cycle, this time on the Jacobian. And you have this Jacobian embedding of C into the Jacobian based at this point C, okay? And you minus the pullback by the multiplication by -1, okay? You have this cycle here, this picture. And this is easily seen to be homologically trivial because when we do the, multiplication by -1 acts trivially on homologic groups or cohomologic groups of even degree, okay? So these are the two cycles that we're gonna study. These two cycles are very closely related to each other. Often we only need to study one of them and you just need to pick your favorite one. Okay, and the goal of our project is to propose a systematic way to study the families, the positivity of the Beilinson-Bloch hat in family. See this happy face here, that we really want them to be happy, they're positive. The starting point is we use the Beilinson-Bloch height to define a function on a suitable parametrizing space. For example, now we have Gross-Schoen and Ceresa cycles. They're defined using curves, so they naturally define functions, genuine functions on the modular space of curves. The first one is the modular space of curves. It maps to the Beilinson-Bloch height of the Gross-Schoen cycle. We call it the Gross-Schoen height function here, and the Ceresa height function. And here are some classical results. First, these two heights, they are well defined and they both vanish on the hyperelliptic locus. So for example, if G equals 2, it's just 0 everywhere. If G is 2. And next, it is known that these two heights are related by this simple relation. The Gross-Schoen height is 6 times the Ceresa height. So in point of view of arithmetic geometry, we only need to study one of them. And usually Gross-Schoen cycles are preferred in arithmetic geometry if you want to study arithmetic, and Ceresa is preferred for geometry. Okay, then we can decompose the question of positivity into more detailed questions in different grades. For example, now we're going to assume G is at least 3 because 1 is 2, it's 0 everywhere. We don't need to study anything. Assume G is at least 3. First question we can ask is this Gross-Schoen height function a dominant height or not? Well, by dominant height, recall that it means that it should have a lower bound and satisfy the Northcott property. But pay attention, because it's 0 on the hyperelliptic locus, it cannot satisfy the Northcott property on this hyperelliptic locus. So when asking this question, we must remove some subset. And so the question becomes, is this the dominant height on a Zariski open dense subset defined over Q? If this is true, this will imply some generic positivity. The second is, can we determine this U? In the sense that given a curve, do we know whether this curve in U or not? And third is this lower bound 0? That's going to answer the positivity question. Yeah. No, it's about the cycle. You mean these facts or? Yeah. These facts, it's because they are explicit in this. Yeah. No, it's not a general thing. Okay. Now here's the statement of our main result. So far, we proved the result for question 1. So we define this ample locus to be the maximal Q-bar Zariski open subset on which HGS is the dominant height. Then question 1 becomes, is the ample locus non-empty? And is it defined over Q-bar? Then this is equivalent statement for question 1. And we prove it. Question 1 holds true. For question 2, we have a partial answer to it. We show that the ample locus can be constructed. But the construction is in some harsh theoretic terms. So given any curve, it's not immediate whether it's in this ample locus or not. But one can show that hyperelliptic locus is outside this one. And also some other concrete families are outside this one. There's a family studied by Laga-Schlittmann. We can show that also this family is outside that. So we still need to express it more explicitly and need to show that the lower bound is non-negative for this project, but at least we have some progress here, especially for part 1. We do have a generic positivity result. That's because it satisfies the Northcott property. So for any number field K by Northcott, there are only finitely many curves in this ample locus with non-positive Gross-Schoen height. So yeah. You mean this one? Yes, actually, we do expect it's never 0 on this locus. We actually do expect it's never 0 on this locus, or it's 0 very sporadically on this locus. This is our expectation. Yeah. So the complement of that, we call it slim locus in our paper. We do expect that the Beilinson-Bloch have vanished exactly on them, or even, yeah, basically it should vanish exactly on them. Yeah.
Is positive automatically open?
Well, sorry?
Is the locus where the height is positive automatically open?
No. It's well, no, not in any topology. Okay. So here is the statement of our from next slides, I'm gonna move to the proof. It's gonna be more technical. So are there any other questions so far at this point? Okay, so now I'm gonna pass to the key steps. Yeah, sorry. Yeah, this is a very good question. So we just define it to be the maximal one, maximal Zariski open one. If you have 2 Zariski opens, you can take the union. It's still another one which is bigger than that. And in the end, there is a sequence which you can show that it's it's a maximal one, right? Because you can take unions. This operation is stable under union. You don't know it whether it stops, but any union of open is still open.
Doesn't have to stop by criterion.
But really, because you can't use dimension to control that, right? Can you use the dimension to control it? Open. Open you can, right? Why not? It's you mean the complement is a closed, and then you take the intersection of them, then they should. Yeah, you're right. Yeah, by some non-serving argument, it will stop. Thank you. Yeah, but at least if you take 2 opens, you take union, it's still an open. Yeah. Okay. Are there other questions? Yeah. Okay. Now let's move on to the key steps of our proofs. So here are the key steps of our proofs with something in the middle. First of all, we need to show that this function, it is not just a function, point-wise defined by something. First of all, we want to find a suitable line bundle such that this function is defined by this line bundle. It's the height function associated to that line bundle. And this line bundle is provided by the theory of idyllic line bundles. I'm going to explain that later on. And then we will prove a volume identity for this line bundle, or for some part of this line bundle, in which we need to use a Morse inequality. And these are the arithmetic part, which using Abel-Jacobi periods and Archimedean heights, local heights, will pass through some geometric part of the study of Betty strata and Betty form, for which we use functional transcendental mixed X-genuine and some O-minimality for period maps. As an organizer of the session, O-minimality and arithmetic aspects of Hart theory, I do want to emphasize a bit this result, the O-minimality of the period map. Jacob Zimmerman is giving lectures in the morning session. This really helps a lot with study of general families by using period maps. because now you have this mild tame topology, which claims that something is algebraic. Okay, now these are the key steps. Now I'm going to explain especially the first two parts. The first result is just the theorem itself is simple. There is an adelic line bundle such that the Gross-Schoen height function is the height function defined by this adelic line bundle. I only want to emphasize here that the construction used is a polarized dynamical system. So it's why it works for Gross-Schoen cycles and Ceresa cycles and not general families. But at this stage, you may ask, what is an adelic line bundle? Probably some of you heard of it for the first time, and probably you don't know it for details. Well, here, to explain the whole thing, you need a course. But now I still, at least I want to explain some of the motivations and ideas behind. Now let's work with height theory. Let's take a projective variety with a line bundle, both defined over a number field K. And now we explain that we have these naive heights given by the embeddings of x into Pn for some Pn. And this naive height, it is well defined up to a bounded function. It is not a genuine function, but it's well defined up to a bounded one. For some purposes, that's enough. But still, we do want to get genuine functions. Just for example, the Néron-Tate height function or the Falting's height. And sometimes this is okay, especially in the Néron-Tate case, when we have some polarized dynamical system. So this is okay. But in general, we can't expect to have something like this. And this is where our Klov geometry comes in. The solution of our Klov geometry to this one is we consider integral models. We take an integral model of x, and then we extend this line bundle to the whole integral model. And next, we put some metrics on the integral model at infinite places, at Archimedean places. In our Klov geometry, they think about spec Z. Spec Z is an affine scheme. It is not projective. It is not compact. And the idea of compactification of spec Z in our Klov geometry is we can identify each close point with a place of Z, and then we add the Archimedean place. So adding Archimedean place is like compactifying spec Z. And in general, if you have a variety over spec Z, arithmetic variety over spec Z, then you have this fiber at infinity on which we put metrics. We use complex geometry to study that. And this is the idea. So we have the Hermitian line bundle. So here we are putting metrics at Archimedean places. That non-Archimedean places is just usual reduction theory, just reduction. This is very good. Now we do have genuine height functions using the arithmetic intersection theory by Gillet and Zoulet. But a caveat is we cannot recover Néron-Tate height for abelian varieties, one of our favorite height functions. We cannot recover that using the theory when A has bad reduction. So we do want to have a theory which unifies both aspects. And this solution was provided by Shouwu Zhang in the 90s for projective varieties. So he instead of putting metrics only at Archimedean places, we also put metrics at all the finite places. So we put KV metric on L of L on any X KV bar points. So we call these line bundles matrix line bundles. This especially works for example, if you have an abelian variety, especially for bad reduction places, we put matrices. Pay attention, so abelian varieties at Archimedean places, they become torus. So somehow they always have bad reduction at Archimedean places, even totally degenerate. And adelic line bundle is not any matrix line bundle, but those ones which can be obtained as some limit of these integral models, I'm going to be very vague on this. You need to fix some topology and so on, but defining adelic line bundle, you can see it as a matrix line bundle, which can be obtained by limits of integral models. So this is the idea of adelic line bundles. in the 90s up to now. And in 2021, Yuan and Zhang extended the theory to quasi-projective varieties by allowing limits of integral models of all compactifications of X. If you have X quasi-projective, you first of all need to compactify X and then consider all the integral models here. And now, pay attention, if we work with projective varieties, if you just forget about all the metrics, then you just get L itself. But for quasi-projective varieties, because we also consider all compactifications of L, even if you forget about all the metrics, you still do some limit. And we get the so-called generic fiber of it. Okay, so for quasi-projective varieties, there's an extra operation here, but still we get a generic fiber on it. And here's an example which explains why it's called adelic line bundle. Take the simplest case, a point. If X is a point and the line bundle is just a one-dimensional vector space, and putting metrics, we're just putting metrics at all the places. That's fine. But saying that it can be obtained at the limit of integral models is this condition. For any non-zero section L, the metric is 1 for all but finitely many places. So this is what this is why it's called adelic. Okay. So this is the idea behind the adelic line bundle, at least from a height theory point of view, why we want them. Okay, now we prove that there exists some adelic line bundle, and recall this is our main theorem. We prove that it's a dominant height on a Zariski open subset defined over Q. First of all, this is defined by a line bundle, and this line bundle satisfies, and we wanted this height to have a lower bound and satisfy the Northcott property. And usually in height theory, these kind of results corresponds to some bigness results of the line bundle. And because we only want any lower bound, so it's more or less like in the height machine. If it's well-defined up to a bounding function, we're fine. So it's only about the generic fiber, and this kind of results corresponds to bigness of the line bundle. So having these two good properties in height theory corresponds to the bigness of the generic fiber of our line bundle. Okay. And big means the volume is positive. Whatever this volume is defined, you can imagine this if in the classical case of projective varieties is defined using some limits of the H0 of powers of L. Here it's similar, except that we need to put some condition. Okay. And the key property we prove here is this volume identity, because we want to prove that volume is positive, then we compute what is the volume. From the point of view of complex geometry, this property is reasonable, because if you have a projective variety over complex numbers, and then the volumes is often computed using this one. And in this particular case, we also prove this volume identity. Actually, we'll prove something stronger, which we need to descend this set. We first of all a priori construct such a set over C, and we need to descend it over Q. For that purpose, we need to prove this volume identity for any subvariety or any subvariety. Yeah.
Could you explain the precise comment or the definition of volume on the left-hand side a little bit? Because the right-hand side is purely over the complex numbers.
Yes. I'm gonna say a bit more here on this slide. Okay. So first of all, the volume if we have a projective variety and a line bundle, then the volume is just you take power, the mth power of this line bundle, you take the global section of that, you count the dimension, and then you divide it by m to that power of the dimension of x and divide it by the factorial of the dimension. So this is the usual case when x is projective. When x is not projective, especially our case, x is not projective, instead of taking just the full group of global sections, you put some extra condition representing the boundary. So it's still the same definition, but for that H0, you need to put an extra condition to say that, okay, it can extend to some compactification of S. Is it okay? Okay, thank you. And actually, this explanation is kind of used in the first remark. The left-hand side is defined using some H0. H0 is invariant under automorphisms of C. And so this is why the left-hand side is invariant under the automorphism of C, and the right-hand side, a priori, it's not. And this is where, this is how we can use this to prove that it's over Q, because the left-hand side is invariant is something defined over Q, but the right-hand side is not. So in the end, we can descend. Yep.
Is here a compact variety?
No, not. That's why I put this tilde. So all these things are called eidetic line bundles. Yeah.
Still a question. For which L are you proving this? Which L is this?
This is this L that represents the Gross-Schoen height that we construct. It's a particular case. It's really this particular case. We cannot prove it for other cases at this stage.
It's still at the later slide. Can you say one or two words on how this is constructed and how the Ceresa cycle goes into the
Actually, we don't construct it for Ceresa cycles. We construct it for Gross-Schoen cycles. And the construction relies, first of all, the polarized dynamical system on the universal abelian variety. So you have this universal Jacobian, and then you take C times C to that. You pull back the Poincare line bundle to C times C. And then you do some difference, because now you have C times C. So you have the diagonal and you have the two partial diagonals. You do the diagonal, the pullback of a diagonal minus the pullbacks of the two partial diagonals. Because this minus thing is a big problem actually for the proof. It's a big problem for the proof. And then you use the line pairing. The line pairing is from this fiber product to Mg. That's why you get, because the line pair for the line pairing, if you have relative dimension 2, you need 3 times this thing to give this pair to push down to Mg. And this is why we constructed for the Gross-Schoen cycle, which is something like a C-cube thing. So you need to pair it for 3 of them. So you see, actually, this construction really relies on this concrete example. Yeah. I'm sorry, I don't think I can say more than that for this talk, but if you like, I can explain to you later after the talk. But here are the crucial ingredients. And then, of course, we need explicit computation to show that this holds true. So the construction is sort of very concrete. And this is why here our proof really relies on this construction. And when we see this volume identity like this in arithmetic, again, in algebraic geometry, we see such volume identities for Neff line bundles. Because this is just a Hilbert-Samuel. Hilbert-Samuel says that if the line bundle is Neff, then the volume is the top self-intersection. And top self-intersection in complex geometry is always this kind of integral. So if we can prove Neffness of this line bundle, then we are done. We just proved it. But we cannot. Just because in this construction I explained, we do differences of line bundles, and we have no control, at least in our construction, we don't see control about the Neffness. It could be a priori negative in some directions and so on. We don't know. Of course, we conjecture them to be Neff, but we really cannot prove it. The solution to this, so in the end, we prove this one just by directly computing the left-hand side. Using the definition, you have H0 of the power, and then you divide it by things. And to bound this H0, we use the Maes-Morse inequality, which has 2 parts. The first part is this kind of Euler characteristic to the alternating sum of H0, H1, H2, and so on. It has a bound, and he also bounds each higher cohomology. But also in this case, we also need this very concrete construction, because we somehow need this convergence to be fast enough. And so the whole proof really relies on the construction. But the key points here, I hope I'm clear enough, that we expect to prove it directly by Hilbert-Samuel, but we cannot because no Neffness is shown. So we compute the volume directly, and to do that, we just bound H0 by using the Maes Morse inequality. And we need something to converge fast enough. Okay, is it okay? Okay, now let me go on. Now with this in hand, we can do some reduction towards our main theorem. For example, I said that this result, except for defined over Q bar, is just this volume is positive on the whole MG. So if we can prove that this C1L bar, which is a 1-1 form, if it is non-negative, it is semi-positive 1-1 form, and the top wedge power on the whole space is non-zero, then we're done, except for this defined over Q. And to get defined over Q, we need to do something more concrete, more careful. We need to show that this form, this top wedge power vanishes on its Zariski closed subset, so that we can use this volume identity. On the left-hand side, we apply automorphisms of C, and on the right-hand side, we also apply automorphisms of C in the end, because this one is defined over Q bar, this one must also be. The idea is like that. So part 3 is used to get something defined over Q bar. So now we're reduced to prove this, Okay. Okay, now let's do a partial summary now. We have proved these arithmetic parts. We're done. And now we are reduced to prove that this 1-1 form is semi-positive. The top wedge power does not vanish identically, and it vanishes on Zariski closed subset. Now, again, this L bar is very concrete. Everything here depends on L bar. Now we do a bridge to the geometric part that we compute what is this C1 L bar in this particular case. We show that it equals the Betti form, something in Hodge theory that is rather canonical, defined by Richard Hayne using the theory of Abel-Jacobi periods by Greenfist. So now this result becomes, you can replace this C1 bar by the Betti form, which I'm going to explain, of course, later on. And then we go to the geometric part and prove the algebraicity of the Betti strata. That's basically this part, algebraicity of that. So we're going to prove that this is Zariski closed, and we're going to prove a checkable criterion for the vanishing of the Betti form. Corresponds to the second part. The fact that it's semi-positive is classical. Now, let me go to the geometric part. Before that, are there other questions? Okay, now let me go to the geometric part. I have 12 minutes left. Okay, now because it works for any homological trivial cycle, so somehow in our project, this part is solved for problem 1. But this part, everything basically relies on the construction and relies on the fact that we work with Gross-Schoen cycles and Ceresa cycles. Okay, now for the geometric part, here is the general setup. We have a family of projective varieties over C. Now it's over C, and we have a family of homologically trivial cycles of codimension n. For example, in the Ceresa cycle, in the Gross-Schoen cycle case, we have the fiber product of CG of the universal curve, 3 powers of that, and Z is a family of Gross-Schoen cycles, and codimension is 2. Codimension is 2. It's 1 cycle, and in 3-dimensional things, the codimension is 2. And the Ceresa cycle example, we have the relative Jacobian, and Z is a family of Ceresa cycles, and now the codimension is G-1. G-1. And now we're going to work with some Hodge theory here. We take the relative cohomology of 2n minus 1. This n is this codimension n. Then every fiber is just the Betti cohomology in degree 2n minus 1. And we know that we have a Dirac-Betti comparison after tensoring C. This is just the Dirac cohomology, so we can use PQ forms to get a filtration on this one, on this space. So we get that VZ is a variation of Hodge structures of weight 2n minus 1. So each fiber is a Hodge structure of 2n minus 1. And also we have a polarization that's restricted to each fiber. We have a we have a bilinear form, and it's positive, negative depending on the pieces. Sometimes in geometry you see this restricted to primitive part, but you can use Lefschetz to extend it to the whole V. And actually for us, it's important to work with the whole V. This is just some technicality from hard theory. Yeah. So we do have this variation of Hall structure from just this family and this N. We have not yet used the cycle Z yet, the family of cycle Z yet. We have a variation of Hall structure. And then comes the result of the construction of Green-Fifth, the nth relative intermediate Jacobian. This example is how you write it down in hard theory, but let's do it in a more concrete way. Let's look at each fiber, what it is. Each fiber is XS, and we put JNXS. It is called the nth intermediate Jacobian. It is a complex torus defined as follows. We take the 2n minus 1 cohomology with C coefficients, and then we quotient out by the middle filtration. We call that we have a hard structure, so we have a hard filtration. We quotient out by the middle piece. And then real analytically, this quotient on the left can be identified with just a real coefficient cohomology. It can be identified to that. And on the right-hand side, we quotient out by the integral coefficient cohomology group. Then here we have a compact complex torus. And if you forget about the complex structure, it's just a real torus. So we have two things. Now, this is a family, a homomorphic family of compact complex tori. And it is also a family of real tori, which becomes a local system because fixing the rank, we only have one real torus. Okay? So this each fiber-wise is like this. And Griffiths proved that we have an Abel-Jacobian map generalizing the usual one from curves. So for the curve, the Abel-Jacobian map from curve to Jacobian is you fix a base point, and then you send any point on C to that point minus the base point. So we can say that, okay, we fix a degree 0 divisor. We fix a degree 0 divisor, that's going to be homologically trivial. And we send it to the Jacobian. So this is a generalization of that to higher cycles, and the construction is similar. You can find co-boundary conditions, find the boundary, and then do integrals and so on. So if we consider Chow group of cycles of codimension n, we restrict to the homological trivial part. It is mapped to a point in this compact complex torus, okay? And this, of course, can be done in family because now enters our family of cycles Z. And this, we call it a normal function. It just sends each point to the image of the Abel-Jacobi map of the fiber. Okay, so the family Z comes only here. Are the definitions, constructions clear? Okay. Now we have this family of compact complex tori, which also is a real local system of real torus, and we have this section of it. So it's a map from S to this family. It's a holomorphic map. Now this is a family version of this identification of compact complex torus with real torus. In family, it becomes this one. The right-hand side is, you see, it's really a local system of real tori. So it's just the family version of that. And now we do two things parallelly. On the left-hand side, we use this mu from S to that. So mu S is a subvariety of that. And we take the differential of that. Now it becomes a linear map from the tangent space to the tangent space here. And next, we use this identification to see that the tangent space here, if we forget about the complex structure here, we get the tangent space of this real torus, a family of real tori. Okay? And this family, it's somehow very flat. is somehow a flat thing. So it's just the direct sum of the tangent space of the base plus the tangent space of the fiber. But we have a torus, the fiber, the tangent space of the fiber is very easy. It's just a real vector space. And then we project it to the second factor. We project it to the second factor. We get a linear map from here to here. And with this in hand, we can finally define what is the Betti form here. Roughly speaking, in brief words, it's just a pullback of a two form here on this vector space to this vector space by this map. And this two form is defined using this polarization, this bilinear map. So this is the actual definition, but it's really just the pullback of the two form here to a two form on S. It's a two form on S. And Richard Hayne proved that this two form, after computation, is actually a 1-1 form, if you consider. So it doesn't have 2 0 parts or 0 2 parts. It's a 1-1 form. And using Greenfield's transversality, it's even semi-positive because the image can only lie in a small piece of that. On the right-hand side, we also can do this all family-wise without doing this projection. So now we have a local system of real tori, then we have a foliation on that. So with each leaf being just somehow a pullback of that, pullback of this thing to this thing, integrable of that. So each leaf is just a piece like this. Okay? And with this foliation in hand, we can define the Betti strata. They are precisely the points on S such that this mu S, this section, this normal function we constructed from the family of cycles, intersect this Betti strata, has dimension at least 1. So it contains some parts of each point will intersect some leaf. And this Betti strata is okay, it intersects this leaf in the positive dimensional thing. And in our project of S, Betti 1 is the most important thing, because when you do these constructions, you will see that the top wedge power is identically 0 if and only if at every point it contains a small part of the leaf. This is almost by definition, because here the form is the pullback, and the pullback and also the foliation, each leaf is sort of the pullback. So this is the reason here. So we have the definition of Betti form and this Betti strata. Betti form is semi-positive. And our result is a simple, using these terms, we've proved that the Betti strata is Zariski closed, because a priori, this thing is only real analytic. And we prove that it's Zariski closed over C, and we have a checkable criterion for it to be exactly S. And equivalently, it's a checkable criterion for the top wedge power to vanish identically. And because it's checkable, so we can check it for each family if you have it. And now let's go back to Gross-Schoen and Ceresa cycles and go back here. Recall that we have reduced our main theorem to these 3 points. And we have proved that the C1L is just the Betti form of the Gross-Schoen cycle. So we have beta Gross-Schoen. And then by this result here, by this theorem applied to this particular case, we have that, well, first of all, the Betti form is semi-positive. This is what proved by Hayne, as I explained before. And secondly, the top wedge power is non-zero. In this case, it's also independent by Hayne in a very different proof, but he doesn't study the strata and so on. So he showed that it's somehow something real analytic. In this particular case. And also we prove that S1 is Zariski closed. And this is actually what they are not exactly the same, but somehow we found out that this is a better thing. This is a better object to study in this story. They differ from some minor size, some meager sets, but in the end, we found that, for example, for the height to be dominant and so on, it's really this S1, S Betti 1, which is important rather than this one. Okay, so now this is done. In the end, again, I restate our main result that we propose this program to study the positivity of Beilinson-Bloch height. We show that if we consider the maximal Q-bar Zariski open subset on which is the dominant height, this set is now empty and is defined over Q. And secondly, it can be constructed in some way, and the construction is using this Betti foliation. So it's not satisfactory. It's not satisfactory enough. We hope to improve that and do some computation, at least when G is small enough. And corollary is a generic positivity using the Northcott property that for any field at K, there are only finitely many curves lying in this ample locus with non-positive Gross-Schoen height. And in this proof, we get some extra results from torsions because this Betti stratum, by definition, the leaves contains all the torsions. All the torsions are leaves. So immediately outside S Betti 1, nothing can be torsion in family. If you have a small piece which is torsion, it must be contained in S Betti 1 because all these leaves are. So we get some non-torsion results for non-algebraic points, which are also independently proved by Hein and Kertayu. So our set is defined over Q. Hein's set is real analytic, and Kertayu's set is over C. Okay, I think I'll stop here. Thank you.
Thank you so much. I like it. If I give you particular one parameter family, what exactly do you do to do this technical condition? That are those that inform that I'm calling everyone around this. What kind of computation we have to do?
Yeah, so it's really in terms of the period maps, and you need to know that first of all, are there any torsion? Is this family completely torsion? If not, then you need to compute like the period maps and manifold groups. Yeah, for Gross-Schoen cycles or for Ceresa cycles, everything can be done explicitly because it's over the whole MG. So basically, the manifold group is SP or GSP, and you know by representation theory what kind of submodules can exist.
I understand correctly, for any normal function, you can construct a beta form.
Yes.
And which is
not us.
But only for the Gross-Schoen, you can construct the M.
No. Okay, so we can construct this S Betti T for any normal function. And we proved for Gross-Schoen that this is exactly the complement of amp. Yes.
The corresponding line belt, is that all? That's not general. That's only for Gross-Schoen.
The general line boundary arithmetic, yes. But in geometry, you always have this by extension. I didn't mention in my talk. So if you want to, for this logic, for example, yes, this L bar is only for Gross-Schoen. This L bar is only for Gross-Schoen, yes.
Thank you for the talk. So I'm interested in the adult line model that you just applied. So I believe there's some like construction using like graph theory. So
yes, you can, but only in this case, there's another construction using graphs. Yeah, but
the question is, like, is there some way to recast or proof your results on the deafness and bigness in terms of graph theory?
We're not sure because here the whole thing is you need to prove this kind of volume identity. We don't know how to prove that using the construction of graph. The construction using graph also was done by Yuan. He explained very briefly in one of his papers. Yeah, but it's unclear how to prove this one using that construction. So
here you show that you want to compute the volume of this dynamic line bundle. Then you translate to compute the volume of something from the family of this intermediate Jacobian. And so I think in the median Jacobian case, here you do not have any other place. You only have the complex place, but you can still from this complex place construct some geometric part of the line model.
Yes.
And is it possible to show that this geometrical part of analytic line model equal to the analytic line model as well?
It's a very good question. It's something we're working on.
Yes. The stage can you can prove the method?
Not yet. Because, well, C1 is semi-positive everywhere, but still you need to understand what the boundary is. And
But you only, what I mean is the analysis of the geometry.
yeah, still the geometric part, you also need to analyze the boundary because here is L tilde, it's not that L. You still need to extend it to small compactifications.
Yes, but I think for the, if you have a family of Beilinson variety and you use this lemon tape structure, then you use this tape, you always get the geometry.
The problem is if you work with, for example, the Ceresa cycle is not the Nihon-Tate family. It's
but in this case, let me see.
it's not a Nihon-Tate family.
But you use this Beilinson fluctuation and if you use this Beilinson current, then I think it always comes from some analytic line model, which is from this.
That's fine, but positivity of semi-positive of our currents is, I don't think it's strong enough in some way, because for example, if you do intersection, I know it's just when you do intersections of currents, it's by general theory, it's not guaranteed to be positive. It could be negative a priori, but you need to exclude that. So the thing we're doing is we try to understand this boundary using some hard theory. Yeah. It's not formal. It's not formal. Even for Gross-Schoen part. Yeah. I mean the geometry for everything over C, you have this by extension things and so on by hint. That's not a problem, but still you need to extend it to the boundary because the base is not compact. You still need to understand how the limit goes to the boundary and so on. Yeah.
Well, I'm sure you already explained it, but maybe I can visit, so can you explain? So we want to prove that open set is like dominant, right?
Yeah.
Explain how the value identity if we resolve that.
It's this remark. So when you want to prove that this is a this height function defined by a line bundle is dominant on its Zariski open subset over Q bar, it is the same as proving that the generic fiber of the line bundle is a big line bundle. So think about also, let's think about the easy case of projective variety that you have a line bundle on it. You want to show that it has a lower bound on the Zariski open set. To do that, what we usually want is you find a section of that line, a global section of line bundle. Then outside the divisor, the support of the divisor of the line bundle, it is dominant. And you don't need to find global section of this line bundle, but any power of that line bundle will work. And this, now everything is over Q bar, it's just a generic fiber. And because here the definition of the dominant height, we just want any lower bound. Even for this genuine function we have, we just want any lower bound. So it is really about the generic fiber of that. So this is why, even though we have this full identic line bundle, which is something defined on let's say, metrized line bundle on sort of integral models and so on, to prove that it's a dominant height on a Q-bar Zariski open subset. It's just the bigness of the generic fiber. And the bigness of the generic fiber is still defined using this volume, because volume is the limit of the H0 and so on. Yeah. So it still got philosophy behind.
Maybe in the interest of time, we can hold all further questions for a break. Thank you so much, Liam.